Welcome to the third in a series of 3 modules on designing out waste. This third and final module will present some case studies to illustrate how designing out waste processes work in practice and how the tools available can be used to deliver effective reductions. The detailed case studies in this module will focus upon 2 projects, the London Olympics 2012 and an affordable housing development in Harrow near London. They show designers how the designing out waste process works on projects at different scales. Some further case studies are presented in summary form, and the module then concludes with a look at the design detail sheets that are available to provide support on reducing waste on specific building elements. Each case study provides examples of using one or more of the 5 principles of designing out waste described in Module 2 of this series. Sometimes, more than one of these principles can be used at the same time, as we will illustrate in the case studies that follow. The hosting of the London 2012 Olympics has given rise to one of the largest infrastructure and redevelopment projects undertaken in recent years in the UK. A wide variety of buildings are being constructed, some permanent and some temporary, each of which throws up particular challenges and opportunities for designers in terms of waste minimisation. The Olympic Delivery Authority established a sustainable development strategy from the earliest stages of the project. This included a headline objective for waste and 3 more specific commitments. The first commitment was on demolition waste measured by weight. The second commitment was on construction materials measured by value. The final commitment was on the use of recycled aggregates, including the associated park-wide infrastructure, in addition to the permanent venues. In order to achieve these targets, action was required throughout the procurement, design, and construction phases of the project. Implementation guidance was produced for all projects teams, which included specific design objectives for waste within each venue brief. A design report template for waste management was provided, together with guidance on the quantification of savings. In addition, targets were set for achieving waste credits under the BREEAM assessment system. Specific requirements for reuse and waste reductions were included within the design team appointments and also for the construction teams through the invitation to tender and ultimately in contract documentation. This was passed down to the appropriate subcontractors by means of package-specific requirements on waste. Recording good practice allows successful strategies to be shared and highlights the waste impacts of design decisions taken for other reasons. The Olympic Stadium, the centrepiece of the Games, showcases this approach as it has many features illustrating best practice in designing out waste. In this slide, we are just focusing on the first of the 5 principles of designing out waste, design for reuse and recovery. For example, 140,000 tonnes of recycled, crushed concrete, originally brought onto the site for use as piling mat, was reused in the permanent works, reducing the quantity of virgin aggregates required, saving £1 million and eliminating more than 20,000 lorry movements. The upper section of the stadium is designed to be removable in case future uses of the site should require a smaller stadium. Standard lengths of surplus gas pipeline were tested to ensure fitness for purpose and then incorporated into the design for the compression truss structure that forms the upper section of the stadium. This reuse of apparently waste material from the gas industry saved 2,500 tonnes of new structural steel, thereby reducing embodied energy and primary resource use and enabling a cost saving of approximately £500,000 to be made. The second principle of designing out waste is to design for off-site construction. 2 examples of this have been achieved at the International Broadcast Centre, also known as the Press Centre, and its car park. The multi-storey car park serving the Press Centre was originally designed as a cast in situ concrete structure. However, during the value engineering process, it was decided to change this to a largely prefabricated solution in concrete and steel in order to reduce the amount of materials and temporary works required, as well as reducing the construction period. In the press centre itself, toilet facilities were designed to be manufactured off-site in a modular form and then simply lifted into place. The contractor and its subcontractors estimated that this would create 70 to 90% less waste than if multiple trades were working together on site. The third principle, designing for materials optimization, can be seen at the new velodrome, which is a cable net roof. This design is lightweight and therefore resource efficient, as it uses significantly less steel than more conventional options. This, in turn, enabled other parts of the supporting structure to be designed for reduced loads. The contractor actively supported the use of a cable net roof, as he was able to demonstrate that this would save 3 months on the project program and reduce the overall cost. The fourth principle, design for waste-efficient procurement, was followed at the basketball arena. Take-back and reuse arrangements for key components were put in place with contractors, and extensive use is being made of equipment readily available on the rental market, such as seating and mechanical and electrical equipment. The weight of the structural steel frame was reduced by 100 tons, approximately 10% of the total, during the detailed design period by selecting lighter members, designing to a higher percentage of structural capacity, and minimizing offcuts during fabrication of the frame components. This produced a saving of £60,000 in material costs. 3,000 tons of recycled railway ballast was used instead of virgin aggregates in the vibro stone columns for the arena's foundations. This foundation technique also produces minimal amounts of excavated material. 80 tons of second-hand steel piles from a local source were also used, contributing to achievement of the project's recycled content target. The last of the 5 principles is design for deconstruction and flexibility. Again at the press centre, which was designed to be a permanent structure, the internal layout is flexible, and the steelwork has bolted rather than welded connections so that it can be easily adapted and ultimately deconstructed. The mechanical and electrical services, which are specifically related to the games, have been separated out so that they can be easily removed afterwards when they are no longer needed. Our second detailed case study looks at a very different type of scheme, a residential development in Harrow, near London, scheduled to be complete in 2012. This development of affordable housing in Harrow is known as Box Tree Lane. It comprises 10 apartments and 4 houses, all designed to Code for Sustainable Homes Level 3 and using the highly energy-efficient passive house design system. The scale is much smaller than the Olympic Park example, as the total contract value is less than £2 million. The design and build contract selected also had the effect of reducing the number of parties involved with responsibility for reducing waste, and allowed integrated waste reduction solutions to be followed through from design to procurement. Box Tree Lane was designed to maximise reuse and recovery. The existing basement was infilled with uncontaminated demolition rubble from the site. This reduced the amount of waste removed from site, but also reduced the amount of infill material needed to be brought onto the site to level the ground. The site had a gentle slope, and rather than levelling the site before construction commenced, the designers worked with the existing slope and varied the construction accordingly. Recycled aggregate was specified and used wherever possible throughout the site, and a minimum 15% recycled content was specified for the other building materials brought onto the site. In addition, an aspirational target of 30% was also included within the design team aims, and there was a particular focus on key materials to achieve this, including foundations, blocks, and windows. The architects at Box Tree Lane also managed to design out waste by using the second principle, designing for off-site construction. All the floor planks in the development were precast off-site, which was more resource efficient and reduced site waste. The balcony balustrades were not only manufactured off-site, but also finished off-site, thereby reducing the number of trades on-site for this element, which granted did not result in a huge waste saving, but was seen as an easy win. Materials optimization was achieved firstly and most effectively by choosing a single block for the external walls of the building, in place of commonly used cavity wall construction methods. This simplifies the design considerably, as it eliminates the separate construction of the internal skin, the introduction of separate insulation material, the need for wall ties, cavity trays, and associated detailing such as weep holes in the external skin. The development was also designed to standard dimensions, so that, for example, window heights are aligned with the dimensions of the blocks used. Internally, the walls were directly plastered, which eliminated 420 sheets of plasterboard and the associated waste. The ventilation system was redesigned, thereby reducing waste through further materials optimization. Ventilation outlets are normally positioned at the furthest point from the door to the room. However, working with passive house standards, if the air has sufficient speed, it will travel across the ceiling and drop down the far wall, so the outlets were repositioned near the entrances to rooms and 144 metres of ducting was saved. The window design was also simplified, as the windows can be cleaned from the terraces, so no tilt and turn mechanism was required. This led to a 10% saving by weight of materials in the windows and a 50% saving on cost. In this case, waste would have been reduced at manufacture rather than on-site. Waste-efficient procurement was achieved at Box Tree Lane through efficiencies in both design and ordering. The reduced palette of materials, principally from the use of monoblock walls, eliminates several waste streams, including packaging. Careful quantification and avoidance of over-ordering on blockwork and insulation in particular resulted in reduced wastage on these products. Lastly, Box Tree Lane has been designed for both deconstruction and flexibility. In terms of flexibility, the 6-bedroom apartment can easily be converted into two 2-bedroom apartments, and the 3-person accessible apartment can be converted into a 4-person apartment. When deconstruction ultimately takes place, this process will be made much easier as the accessories and finishes have been mechanically fixed rather than glued into place. We are now going to look briefly at 2 final examples of projects where designing out waste was employed: the Calderdale Leisure Centre and Mansfield Community Hospital. The Sowerby Bridge Leisure Centre in Calderdale opened in 2010 and achieved a BREEAM rating of good, including gaining relevant credits for waste reductions as a result of the following activities. An accurate assessment of material requirements was conducted to reduce over-ordering. Ducting is often installed and then insulated, but in this case, the design team selected pre-insulated ducting, thereby saving £6,000 in materials costs and reducing installation time. Rather than casting concrete stairs in situ, staircases were cast off-site, thereby eliminating the formwork that would have been required. Packaging waste was also reduced, particularly for bricks, as these were delivered with metal strapping rather than the normal strapping, polythene wrapping and pallets, thereby saving nearly £1,000 and, just as importantly, 6 tonnes of waste. The redevelopment of Mansfield Community Hospital is our final example of how the principles of designing out waste can be applied. A retaining wall was required to support a new car parking area. The original proposal to build an L-shaped reinforced concrete structure was replaced with a geosystems-based modular block wall, which incorporated a reinforcing grid to stabilize the ground behind the retaining wall. An initial comparison of the two options shows little cost difference, although the geosystems option had significantly less embodied CO2. So why was the geosystem favoured? This diagram shows the revised wall design. Note in particular the layers of granular material compacted over the geogrids. The contractor was able to screen and process waste arising from elsewhere on the site that would otherwise have gone to landfill in order to produce this material. This is a good example of the dual benefits available from materials optimization: a reduction in materials brought onto site, together with a reduction in waste taken off-site. It was calculated that for the conventional reinforced concrete wall, 507 tonnes of unsuitable material would have to be disposed of to landfill, and an equivalent amount of primary granular fill material imported to make up the ground to founding levels and provide suitable backfill to the wall. This significantly increased the cost of building the reinforced concrete wall. By utilising the materials available on site, no waste disposal or import of fill material was required for the geosystem wall, meaning the cost remained at £26,000, producing a saving of £38,000 over the original proposal. All of the case studies that we have been looking at, together with many more, are available on the RAP and Zero Waste Scotland websites. In addition to the whole project case studies, there are a number of individual design detail sheets that provide guidance on how to reduce waste for specific building elements. The guidance sheets in this series highlight a selection of alternative design details which use less materials or can result in less waste being created than standard details used in construction. The benefits provided by the alternative design details are quantified and technical considerations presented. RAP has also produced an evidence-based report to accompany each of the design detail sheets. The design detail sheet for aerated blocks with thin joint masonry highlights the varied benefits of this type of system. Being 70% lighter than conventional concrete blocks, they are easier to move around site and quicker to lay. They also have 42% less embodied carbon than standard blocks of equivalent size. As these blocks can be laid with thin joint mortar, the amount of mortar used can be reduced by up to 80%, delivering further embodied carbon benefits and setting much quicker than conventional fat mortar joints. The modest extra cost of materials is offset by reductions in construction time and reduced costs of waste disposal. Castellated and cellular beams can achieve the same strength as solid I-beams of the same depth with significantly less steel use, resulting in lighter weight and between 25% and 50% less steel. Castellated beams are created by cutting along the length of the section in a waveform and welding the two pieces to form a deeper section with hexagonal openings. Cellular beams are formed by using precision cutting techniques to produce circular or oval openings. These beams are particularly suited to long span applications with light to moderate loadings such as roof structures. In addition to cost and carbon savings, there is a corresponding reduction in transportation costs and a further reduction in mechanical and electrical materials where services can pass straight through the beams. Voided biaxial slabs are a resource-efficient design for concrete slabs by incorporating voids which significantly reduce overall materials use. Typical systems use hollow plastic spheres placed in a precise modular grid. These can be fixed in place using only reinforcement mesh. The reduction in weight of the slabs also delivers material savings throughout the building structure, principally beams, columns, and foundations. As with castellated beams, there are corresponding reductions in transportation costs, plus reductions in lifting costs and construction time. That brings us to the end of this third and final module in the Designing Out Waste series. So to recap this module, we first examined detailed case studies where all the 5 principles of designing out waste were applied in a systematic manner using the design team review process. We highlighted the savings, both in terms of cost reduction and reductions in waste, together with other savings available in terms of transport impact and time on site. Finally, we then looked at 2 summary case studies available on the RAP website and introduced the design detail sheets, which can be applied to reduce waste on specific building elements. That concludes the last of the 3 modules in the Designing Out Waste series. Thank you for listening.